Okay, so we're going to look at using differentiation to determine stationary points and their nature. That is, if they are maximum, minimum, or points of inflection. To do that, we first need to differentiate this function, and to do that we always bring the exponent to the front and multiply by the coefficient, and then decrease the power of that exponent. So this question is in Leibniz notation, so I'm going to continue that way. So dy dx is equal to, bring the 2 out the front, so negative 2, decrease the power, so negative 2x on 2 minus 1, okay, because there's a 1 power here. 1 times negative 1 is negative 1. Once we decrease the power, the variable disappears, and this doesn't have any variables. So if we simplify that by cancelling out the 2's, we end up with dy dx equals negative x minus 1. So that's the equation of the differential, or the slope, whichever you wish to refer to it as. Now for the stationary point, we need the slope to be 0. So we need to equate that to 0 and then find out what x equals at that point. This one's quite straightforward because it's linear, so we're just going to move the 1 to the other side. So it'll be plus 1 because that's the opposite of negative 1. You get negative x equals negative 1, which is the same as saying x equals negative 1, because we want these to be positive. So at our stationary point, x equals negative 1. Now because it's a quadratic, as determined by this exponent, the maximum turning points we can have is 1, because it's always n minus 1, so we don't need to find any others. Now to determine the nature of the stationary point, we need to have a look at a number below and greater than this x value. So I'm going to do negative 2 and 0. And all I'm going to do is substitute them into my equation and determine the slope at those points. So for lesser than, I'm going to put negative 2 where I see x. So it's going to equal negative 2 minus 1, which is 2 minus 1, which equals 1. And now I'm going to substitute my 0. So I just get 0 minus 1, which equals negative 1. If I have a look at these numbers, this is a positive slope, so it's increasing, and this one is decreasing. Now what does that mean in terms of the nature of the stationary point? So a maximum is always a curve at its highest point for that part of the function. So when the slope is below 0, so it's 0 at the stationary point, it's going to be increasing or positive, and then it's going to decrease or be negative. That is for a maximum stationary point. A minimum stationary point is the lowest point in that region of the function, so it's going to have a negative slope before the turning point or stationary point, and it's going to have an increasing slope or positive slope after the stationary point. Now there's one other type that looks like this. That is a stationary point, and we call it a point of inflection because the slope doesn't change on either side of the stationary point. So if it's negative here, that is before the stationary point, it's also negative after. Or if it's positive before the stationary point, it's also positive after. That is when you know you have a point of inflection. So what do we have? Ours goes up and then down, so it's going to be a maximum, but we need the coordinate. Okay, we only have our x value, so let's plug that in and find our y value. To find your corresponding y values, you use the original equations. I'm going to substitute negative 1. So I get negative 1 squared on 2 minus negative 1 minus 5 on 2. And that's just going to equal negative a half plus 1 minus 5 on 2, which equals negative 2. Therefore, my stationary point is at negative 1, negative 2. Now we already determined it was a maximum, and if you wanted to, you could find your corresponding y value for these 2 points to sketch it, or you could put it into a graphics calculator. So to answer the question in its entirety, the stationary point is a maximum at negative 1 and negative 2, and you can see that here on the graph. The function is increasing when x is less than negative 1 and decreasing when x is greater than negative 1. So here's another example. It's a higher order function, it's a cubic. So first, Same thing, we need to differentiate it. So this is using Lagrange notation. So for consistency, I'm going to use the same notation, bring the 3 to the front, multiply it by that coefficient, so it's negative 3x, reduce this power by 1, bring this to the front, and reduce the power by 1, and this one does not have any variables, so that is your differentiated function. Now to determine your stationary points, you need to find when that equals 0. So negative 3x squared plus 2x has to be made to equal 0 and solved. They both contain x, so I'm going to take that out the front. Therefore x equals 0 and negative 3x plus 2 equals 0, which gives me x equals 2 on 3. So these are your two x values that give you a slope of 0, which is your stationary point, and I'm just going to put them in here. So now I just need to choose some x values that are lesser than this stationary point, so I'm going to go with negative 1. Then I need to choose one that's between the two stationary points, because they're not the same stationary point, so it's not a point of inflection. So it's between 0 and 2/3, so I'm going to go with 1/3, and then something that's greater than 2/3, I'm just going to choose 2. And then I'm going to substitute each of these three values to see the behaviour of the slope. So I'm going to start off by substituting negative 1. That's the behaviour of the slope we're looking at. We are using the slope equation. So I'm going to put my negative 1 wherever I see x. So that's just negative 3 minus 2, which equals negative 5. So that is going to be a negative gradient or a negative slope. Next, I'm going to substitute 1/3. That's the same as before. We just copy the equation. Wherever you see x, you put 1/3 instead, and then calculate. So 1/3 squared, I just square the numerator and the denominator. I get negative 3 times 1 over 9 plus 2/3. If I put the negative 3 on the top, I end up with negative 1/3 plus 2/3, which gives me 1/3. So that is a positive slope. Then we have a stationary point, so it's straight, 0 slope. And lastly, I substitute the 2 in. That's negative 3 times 2 squared plus 2 times 2. It's negative 12 plus 4, which equals negative 8. And that is a negative slope. So that tells us that it looks something like this. We don't know these points, but we can substitute our x values in to find the corresponding y values, and we must do that for our stationary points anyhow, because that is what the question is asking for. So let's find the first stationary point. So we know x equals 0. Because we've already used the slope and we want the actual value according to the original function, we need to substitute into the original function. So f of x, or your y value, is just going to be 0 plus 0 plus 4. So your first stationary point there is at 0 and 4. And now we're going to do the second one of 2/3. So substituting that into our original function. And that gives us 112 on 27, or for those who prefer decimals, it's 4.15. So you can see the two stationary points here, and you can see that the function is decreasing at these 2 points. So we have written that when x is less than 0 and greater than 2/3, and it's increasing when x is between 0 and 2/3. And that is how you find stationary points and their nature using differentiation.